So we might all be breathing a sigh of relief because that's over. We also might be breathing a sigh of, oh shit, because that was just the lemma. We still have the big claim to prove. But as I've said before, lemmas are the unappreciated bros of math, right? And a good lemma basically usually make a theorem super easy. It just goes, once you have that, it's a foundation, and the rest comes easy. So how are we possibly going to use this lemma in a proof? Here's the idea. So, aside. Once again, actually, yeah. So for this guy, what are you guys thinking? Direct proof, contradiction, contrapositive? Contrapositive doesn't even make much sense because there's not an if then here. Like you could get an if then if you really wanted to, but you could change this to say like there exists a Q. Actually, no, yeah. It doesn't really make sense. So really contradiction or direct proof is the question. In this case, it turns out it's not going to even matter. It really doesn't matter. Sometimes the difference in direct proof and contradiction isn't really anything because it's kind of just as hard. You'll see why in a second. So anyway, oftentimes it matters, but in this particular case, it doesn't really matter. And so here's the idea. Here's the brilliant idea. Let's just let n be any integer, and then consider any list of primes in our set of primes. Of length n. So this is basically any arbitrary finite list of primes. Our goal is to show this cannot possibly be all the primes. There's some prime missing from this. How can we possibly do that? Well, basically, right, primes are the atoms of numbers, right? So we have to show that there must exist some number, right, where one of their atoms is not on this list. So we need to show a prime, or even better yet, all of the atoms are on this list. So it would suffice if we found a number that's not divisible by any of these things. Because if that number is not divisible by any of these, right? I'll say note, if there exists a B and Z such that P1 doesn't divide B, P2 does not divide B, and Pn does not divide B, if they all don't divide B, then by the fundamental of the arithmetic, B can be written as the product of some list of primes, but because all of these don't divide B, they can't possibly be in the decomposition, meaning that all of these are not on the list. So if we found a number that wasn't divisible by any single one of these primes, then the primes in this decomposition can't be on the list because Q1 does divide B. So it can't be P1, it can't be P2, and it can't be Pn. And we just showed that just shows that this is not a complete list of primes. So how can we possibly find a number not divisible by anything on our list?
Can we do the lemma where it's a plus 1?
That's a good idea. Note, for example, P1 divides P1. So P1 does not divide P1 plus 1 by our lemma. But theoretically, P2 might divide P1 plus 1. Or P3 or P4 or Pn, you know what I mean?
Well, if we assume that P2 or P1 divides P2, then we can prove that P1 doesn't divide P2 plus 1, right?
Well, are you saying if we assume this?
Yeah, if we assume that, and then we
well,
could just...
P1 divides P2. P2 is not even prime because that's a non-trivial divisor, right?
Oh, right. Yeah. Yeah.
So that's a good point, though. If P1 divides A, then P1 won't divide A plus 1. If P2 divides A, then P2 won't divide A plus 1. If Pn divides A, then Pn won't divide A plus 1. So what if there was a number divisible by all of these? If there was a single A divisible by all of these primes on the list, then the A plus 1 certainly won't be divisible by any prime on the list. Which is exactly what we want, because then that shows there is a number that's B-like, where it's not divisible by any primes on the list, and so it's fundamental theorem of arithmetic shows that it has primes on the list. So can you think of a number that's divisible by all of these?
Is it just the product of all those numbers? All those
Why
primes?
not? Why not? Yes, Justice, fantastic idea. Why not let A equal P1 times P2 all the way out to Pn? No, remember this is a finite list. So we're multiplying finite numbers. So this is an integer. This is fine. But then P1 divides it, right? Because it's a multiple of P1, because you just take P2 out to Pn. P2 divides it, just take P1 times P3 just P4 out to Pn. P4 divides it, all the primes on the list divide it, so none of them will divide A plus 1. So in the prime decomposition of A plus 1, right, we get some other primes that aren't on this list. So it's not a complete list of primes. I'm not noticing a static celebration. This is crazy. This is it. We just did it. Justice's idea just sealed the deal. Thank you, Justice. Does this make sense? Does it make sense, people? We just proved, think about this, people. Think about where we started at the beginning of the year. We just proved that there are infinitely many primes, which doesn't sound as impressive as we proved that for all of the insanely many possible finite prime lists, there will be a prime on that list. That's crazy. Think about how many possible prime lists there are. Just with 10 primes, right? You have what? 10 factorial possible prime. Well, actually, no. You see what I'm saying, though? There's a lot of possible. There's a lot of possible prime lists. But we just did it. Just by kind of following our nose a little bit and using properties of these numbers, you can see that these properties work out in this way.